So in this video, I wanted to discuss U-substitution a little bit and kind of give some examples of problems where U-substitution might come up, and then also how to, solve those problems. So let's start with this first problem here, the integral of 25 sine 3x dx. So the first thing that I would do, well, let's think about this for a second. I see 25 sine 3x. I know the integral of sine x, it's negative cosine x, but I don't know exactly what the integral of sine of 3x is going to be. So we can do a U-substitution here to make things a bit simpler. So let's let u equal 3x. Then du by dx is equal to 3. So that's just taking the derivative of both sides. Now we can use this mnemonic to figure out what our dx is in our U-substitution. So I can multiply both sides by dx and get that du is 3 dx, or I can divide both sides by 3 and get that dx is du over 3. Now, I have everything I need to make my substitution. This is going to be my u here, my 3x, and this dx becomes du over 3. So under the substitution, I get that this is the integral of 25 sine of u times du over 3. So this is the same as the integral of 25 over 3 sine of u du. And then I can just pop this constant out here. So this is 25 over 3, the integral of sine of u du. Now, like I said, the integral of sine of u is going to be negative cosine of u plus c. So that tells me that my final answer here is going to be 25 over 3 negative cosine of u plus c. Now, remember that my problem is asking about x. We're talking about x and dx, so we need to put things back in terms of x. So we will substitute our 3x back in for u. So this tells me that my final answer here is negative 25 over 3 cosine of 3x plus c. Okay. So that is how I would carry out U-sub for that problem. Now moving on, a little bit trickier of an example. So another way we might use U-substitution is if I'm trying to cancel out a function in the integrand. So I'll just show you what I mean here. Let me let u equal x squared plus 3. If I pick this to be my u, then du by dx is equal to 2x. And what I'm going to do is, this is legal. I can swap the dx and the 2x and get that du over 2x is equal to dx. Now I can make my substitution here. This integral becomes the integral of 7 x, actually let me write it like this, 7 over x over, 7 times x over u, because u is x squared plus 3, times du over 2x. Now this x and this x will cancel, and so I'm left with the integral of 7 over 2u du. I can pull that 7/2 out and get that this is the integral of 1 over u du. And the integral of 1 over u is just ln absolute value of u. So this becomes 7/2 ln absolute value of u plus c. Now I got to remember to plug x back in, or rather x squared plus 3. So that's going to be 7/2 ln the absolute value of x squared plus 3 plus c. Now if I wanted to make things nice and pretty, I can get rid of this absolute value sign, because this x squared plus 3 is always greater than 0. So that would be like that. And this would be my final answer. So that's another way we can use U-substitution, is to cancel something out with the derivative that we get by substituting dx for du. And I'll look at an example now of a definite integral that requires U-substitution. So I want to cancel something out, so I see that sign there, and I know that the derivative of cosine is negative sine. So let's let u be cosine squared. Sorry, just cosine rather, cosine theta. Then du by dx is equal to, d theta is equal to negative sine theta. Then that tells me I can just swap these, completely legal, that du over minus sine theta equals d theta. Now, I have everything I need to make my U substitution, but I can't forget my bounds. So when I do a U substitution, I have to switch my bounds when I do the U substitution. So when U is equal to cosine theta, pi over 3, U evaluated at pi over 3 is cosine of pi over 3, and that is 1/2. And U of 0 is equal to cosine of 0, which is 1. So that tells me that my bounds on my integral are from 1 to 1/2. So this is the integral from 1 to 1/2 of, let's see here. So my U is cosine theta, so I get U squared. And then I have my sine theta. And then my d theta becomes du over minus sine theta. This sine theta and this sine theta will cancel. And so what I'm left with here is the integral from 1 to 1/2 of negative u squared du. Now remember, I can switch the bounds here to be in the correct ascending order, I guess, by using this negative sign, because when I flip my bounds, I gain a negative sign, so it'll cancel out with that negative sign I already have. So this would give me the integral from 1/2 to 1 of u squared du, and that's just going to be 1/3 u cubed evaluated from 1/2 to 1, and that's going to be 1/3 times 1 cubed minus 1/3 times 1/2 cubed. So this is going to be, let's see here, I got 1/3 minus 1 over 24. That's the same as, let's see here. So I give these a common denominator by multiplying both sides of this 1/3 by 8. And then that gives me 8 over 24 minus 1 over 24, which is going to be 7 over 24. And that's my final answer. So to review, what I did is I did my U substitution, but I also had to evaluate my bounds here at U. So that's what this part was me getting my new bounds. And then I get my nice cancellation, and I only have to evaluate things in U. I never have to go back to X if I do it this way. Okay, so next I wanted to look at some kind of general cases. And this is kind of what I've been discussing before, but you see it in a little bit more general language here. So the two kind of cases that I really want to use U substitution is if I have a case like this, where I have a function of a function times the derivative of the inside function with respect to the same variable. So you see that this function has, on the inside of this outer function, has its derivative on the outside. So if I let u equal that inside function, f of x, then du by dx equals f prime of x. And that means I can swap these. Du over f prime of x is equal to dx. Now I can make my substitution here. This becomes the integral of g. Remember, f of x becomes u, so it's g of u. And then I have f prime of x, and my dx becomes du over f prime of x. These two copies of f prime will cancel, and I'm just left with the integral of g of u du, and hopefully I can solve this guy to get a final answer. So that's one of the useful ways to use u-sub. The other is if I have a linear function in my function, or in other words, it's not just f of x, I have f of something x. So if I let u be that something, the inside here, ax plus b, where a and b are constant, then du by dx will equal a. Then I have that du over a equals dx. So this integral now becomes the integral of f, remember ax plus b is my u, times dx becomes du over a, and now this just reduces to 1 over a times the integral of f of u du, and that's much easier to compute. And that wraps up everything I want to say about U substitution.